Hey there, everyone. Here we are at the start of week 2 of online learning. So I hope you're doing well. Hope you're kind of adjusting to the new rhythm. Me trying to get up these content videos on Mondays and Wednesdays so that you can watch them in anticipation of our live Tuesday, Thursday sessions where I work through examples. Please let me know if you have any feedback. I'm very open to making adjustments as I need to. We're all figuring this out together, but I'm glad to have you along for the ride, and I'm very glad that I've had some feedback that you're adjusting to this rhythm, but please let me know if there's anything else I can do. But with that, let's jump right in and get going with today's new content.
I want to start with a quick summary of where we ended last week. We spent two classes discussing approaches to hypothesis testing about a population mean. So a null hypothesis that's of the form mu equal to mu naught. Now, regardless of what the alternative hypothesis looks like, and also regardless of whether you're using a rejection region or a p-value for your test, there are a couple of basic principles that you want to follow in determining if you are using the correct test. This flow diagram should look familiar because we saw a very similar version of this when we were discussing confidence intervals for a population mean. The first question you want to ask is whether or not the population is normally distributed. If you do have a normal population, then it's important to determine whether the population variance is known or whether you're using the sample variance in your test. Normality and known variance results in using a z-test. Normality and unknown variance results in using a t-test. In both of those instances, the test you are using is exact. On the other hand, if you do not have normality, but your sample size is large, you can base a test on a population variance or on a sample variance in your test statistic. Either way, you'll be doing a z-test with the knowledge that your test at this point has become an approximation. And finally, if you do not have normality and if your sample size is not large enough, no test will be possible. So this is a big picture overview of what we covered last week. Now let's jump back into chapter 8 and expand on this idea a little bit. So today we're looking at testing a hypothesis regarding a population proportion. So let's say that a certain proportion P of our population satisfies a criterion of interest. This could be what proportion of people who live in Fort Worth work outside the city limits, or it could be what proportion of students who attend TCU are actually out-of-state students. The way data collection works is you collect observations or random variables x1 through xn, where each x value is either going to be a 0 or a 1. A 0 indicates that the sampled unit does not satisfy the criterion of interest, and a 1 is used to indicate that it does satisfy the criterion of interest. At this point, we now have the data we need to test a hypothesis about the quantity of interest. So our null hypothesis is going to be of the form that the true population proportion P is equal to some specified value P naught. And of course, there then has to be an alternative, which is either a partial or a complete negation of the null. And the alternative hypothesis here can have three different forms. Complete negation would just be P is not equal to P naught. But the two partial negation options could be that P is greater than P naught or that P is less than P naught. And these just determine how you calculate your rejection region, or how you calculate your p-value. Now, if you are testing a hypothesis about a proportion, then it's important that your sample size be sufficiently large. This is an approximate calculation, and specifically, we're trying to invoke the central limit theorem here as well. So at least for the purposes of this class, again, when is the sample size large enough? Well, generally, if you do the check that your sample size is at least 30, for the purposes of this class, we will consider that a large enough sample size. If this is what you have, then you can calculate your test statistic, Z observed, and the test statistic is given by p hat minus p naught divided by sigma naught over the square root of n. And that sigma naught value, well, we calculate the square of that value as p naught times 1 minus p naught. So let's just run through what the different aspects in this test statistic are. The p hat, that's your sample proportion. So in your sample with n observations, you're going to count the number of successes, divide that by sample size. P naught is the value under the null hypothesis, and that value is also used to calculate sigma naught, and of course you know what your sample size is. Now, if the sample size is large enough, then this test statistic can be evaluated using a standard normal distribution as a reference. So we are essentially in case 2 of the z-test, where we don't have normality, but our sample size is large enough. And if you want to formulate all our content as a test about a population mean, you can do that. The fundamental mind shift is, instead of working with mu naught, you're working with a value p naught, and instead of working with variance sigma squared, you're working with a quantity p naught times 1 minus p naught. But if you make this substitution, then all the formulas that hold for case 2 of testing hypotheses about a population mean carry over to testing hypotheses about a population proportion. So whether you're trying to do an approximate power calculation, whether you're trying to find a rejection region, we can use all of those formulas and make this appropriate substitution. So we'll dig in tomorrow and do a couple of examples illustrating exactly how we do this in practice. The last section in chapter 8 is just looking at some important concepts relating specifically to hypothesis testing. So digging into some of the detail a little bit. First question we're going to answer is, when should we use a confidence interval and when should we use a hypothesis test? Clearly, there's a relationship between these two approaches. And in fact, it is possible to substitute one for the other. So let's talk about this in a very general sense. Let's say that there is some population parameter, theta, that we're interested in. Theta here is just a placeholder. It could be the population mean mu. It could be a population proportion p. Now, if we have the ability to construct a confidence interval for this quantity, let's say we construct a confidence interval that ranges from theta hat L as the lower bound to theta hat U as the upper bound of the confidence interval. And this interval has confidence level 100 times 1 minus alpha %. Well, if you use this confidence level and you then compare it to testing a hypothesis. Say we're testing the hypothesis that mu is equal to some specified value mu naught. How do these compare to one another? Well, there's an equivalence here that generally holds up. The null hypothesis that mu is equal to mu naught will only be rejected against a two-sided alternative at a level alpha if the corresponding 100 times 1 minus alpha percent confidence interval does not contain theta naught. This is a whole mouthful, but what this statement is telling you is that you will generally have consistency between the conclusion you reach doing a formal hypothesis test and the conclusion you reach evaluating a confidence interval. This statement tells us if our confidence interval contains the value theta naught, then we will not reject our null hypothesis if we do a hypothesis test. Conversely, if the confidence interval does not contain the value theta naught, then at the same level, we will reject the null hypothesis. Now, there are some finer details here. The confidence interval and the hypothesis test have to be based on the same underlying set of assumptions and the same test statistic. But for the purposes of this class, that is generally what we'll do. So a confidence interval and a hypothesis test should not, in the examples that we've discussed so far, lead to contradictory results. The statement that I wrote down here, I can also reformulate that a little bit, and we can say, if the above null hypothesis is not rejected, then what we know is that the confidence interval that's constructed at the same level will contain the null hypothesis value theta naught. So this is just to give you a big picture overview of the connection that exists between confidence intervals and hypothesis testing. The last topic for today is a fairly important one, and that has to do with when we evaluate multiple hypotheses. So in many studies, it's common that researchers have formulated more than one null hypothesis, and they want to test all of these hypotheses. But you have to be very careful how you then choose your significance level. Specifically, let's say that there are k different hypotheses, and these are all independent of one another. So we either know that they're based on samples that were independently collected, or we know theoretically that these tests do not affect one another in practice, that even if we're evaluating them on the same data, their results are independent. And let's assume that each of these k hypothesis tests is conducted at a significance level of alpha. Well, the overall significance level is then defined as the probability that at least one type 1 error occurs. So what is this value? What is the probability of having at least one type 1 error? In other words, what is the probability that if we're doing k tests, that at least one of them, the null hypothesis is rejected when it should not be rejected? Well, this statement is equal to, if we take the complement, 1 minus the probability of having no type 1 errors. And because the tests are independent of one another, the probability of not having a type 1 error for an individual test is 1 minus alpha. And by independence, we can raise that to the power, the number of tests that we're evaluating. So if we call this quantity alpha star our overall significance level, then that is equal to 1 minus alpha to the power k. Now, what you'll notice if you look at that quantity is since 1 minus alpha is a fraction, when we raise that to the power k, that value decreases. So alpha star approaches 1 as k gets large. Think about that for a moment. If we're doing a large number of tests, then the probability of having at least one type 1 error eventually goes to 1. So if we just pick alpha the way we normally would, then we're going to be in trouble. The way you want to approach this is you want to specify beforehand what the overall significance level is. So if you specify beforehand what alpha star is, your overall significance level, then I can solve in that previous equation and show that my individual test level should then be given by 1 minus alpha star to the power 1 over k. And this is how you want to choose your individual test alpha level if you're doing multiple tests and they are independent of one another. The independence assumption here is a fairly important one. There is a way to make an adjustment if we do not have independence. So if you aren't sure that you have independence, then the best we can do is get an upper bound. What we know in this instance is that the probability of at least one type 1 error will be no greater than k times alpha. And so if we don't have independence, this is now the quantity that we define to be alpha star. But what this means is if we're using this upper bound, then our individual test level alpha should be chosen as alpha star over k. So this is how you will choose your individual test level if you cannot make the assumption of independence. And again, in our live session tomorrow, we'll do some examples looking at how this adjustment compares for independent versus not independent. But with that, I'm wrapping up for today, and I will talk to all of you tomorrow.